Welcome to The Explainer. Today, we're going to pull back the curtain on the mathematics that powers, well, pretty much everything. We're talking about your weather forecast, the special effects in your favorite movie, the whole shebang. It's the hidden engine behind our digital reality. And it all kicks off with a really clever workaround.
So, have you ever stopped to wonder how we do it? I mean, how do computers, which are really just super fast calculators, manage to simulate something as complex and, continuous as the flow of air over an airplane wing? The real world doesn't happen in neat little steps, right?
Well, the answer is kind of mind-blowing. We basically cheat. We take the beautiful, impossible calculus that describes the universe, and we chop it up into millions of tiny, simple arithmetic problems that a computer can solve in a heartbeat. We just approximate. To really get a grip on how we build these simulations, we've got to start with the language of physics itself. And let me tell you, that language is both incredibly elegant and incredibly hard to work with. And that language is the partial differential equation, or PDE for short. Now look, I know the equation itself can look a little scary, but don't worry about that. The key thing is what it does. Think of it like a universal rulebook. It doesn't just tell you the temperature in one spot, it gives you the exact rule for how heat flows from any point to its immediate neighbors. Everywhere, all at once. These are the fundamental rules of the game. And what's super fascinating is that these equations come in different flavors, each one perfectly suited for a specific kind of physical problem. You've got elliptic equations for when things have settled down and reached a steady state. You've got parabolic equations for things that are changing over time, like heat spreading out. And then you have hyperbolic equations, which are all about waves. Each type needs its own unique approach. Okay, so if these equations are often way too hard to solve perfectly, how in the world do we build simulations? Well, this is where the clever trick comes in. We basically decide that perfection is the enemy of getting things done. Instead, we make a simplified map of reality. The big idea is this. We replace the smooth, continuous, infinite world with a finite grid of points. It's genius. Instead of trying to calculate a value for every single one of the infinite points in space, which is impossible, we just agree to solve for the values at these specific grid points, these nodes. We literally pixelate reality. This whole strategy is called discretization. So first, you lay down your grid. Then, for every single point on that grid, you swap out the complicated calculus, the derivatives, for a simple algebraic formula. And that formula only cares about the values at its immediate neighbors. And just like that, one impossibly massive problem turns into millions of tiny, easy problems that a computer absolutely loves to solve. All right, so we've got our grid. Now we need a way to actually do the approximating at each point. And this is where we open up our toolbox of methods. Turns out there are a bunch of different ways to cook up these algebraic approximations, giving scientists and engineers a whole set of tools to choose from. The three most basic tools are called finite difference methods. Think of it like this. To figure out how steep the ground is where you're standing, you could look at the point just ahead of you. That's a forward difference. Or you could look at the point just behind you. That's a backward difference. Or, for a much more accurate balanced view, you could look at the points on both sides of you. That's a central difference. And this leads us to a really crucial choice in how we move forward in time. With an explicit method, it's like watching a line of dominoes fall one by one. You can calculate the future of each point directly, because it only depends on the past values you already know. Easy. But with an implicit method, it's like trying to predict how the entire line of dominoes will settle all at once. The future value of any point depends on the future values of all its neighbors, which means you have to solve for everything together as one giant system. So this whole process of approximating things, it raises a huge question, right? How do we know if our simulation is actually correct? And maybe more importantly, how do we make sure it doesn't just spiral out of control into complete nonsense? This is the core challenge, balancing accuracy with stability. But here's the beautiful thing. Our approximations can get ridiculously close to the real answer. That black line you see, that's the perfect, true solution we can never actually calculate. The colored lines, those are our approximations. And look what happens. As we make our grid finer and finer, adding more and more points, our answer gets closer and closer to reality. It's an amazing concept called convergence. So this brings us to what we call the engineer's dilemma. Explicit methods, they're fast, they're computationally cheap, but, and this is a big but,
they can be unstable. If your time steps are too big for your grid size, the tiny errors in each calculation don't just add up. They multiply, they snowball, they grow exponentially until your entire simulation just explodes into digital gibberish. On the other hand, implicit methods are rock solid, unconditionally stable. But that safety comes at a steep price. You have to solve a massive system of equations at every single step, which is way, way more expensive to compute.
Okay, so after we've picked our equation, designed our grid, and chosen our approximation method, what's the final step? Well, now it's time to actually solve the massive puzzle we just put together. So all those simple algebraic equations we made, one for every single point on our grid, they all get bundled together into one enormous matrix equation. This one matrix basically represents the entire state of our physical system at a single moment in time. You solve this matrix and bam, you get the temperature or the pressure or the velocity at every single point on your grid. And even here, you've got choices. You can use a direct solver, which is kind of like following a very precise recipe to get the one single perfect answer for that matrix. Or if your matrix is just too huge, you can use an iterative solver. That's more like intelligent guessing. You start with a guess, and then you keep improving it over and over again until your answer is good enough. So at the end of the day, that's the whole game right there. That's the big takeaway. We trade the elegance and perfection of continuous math for the practical, raw power of discrete, solvable approximations. And it's this fundamental trade-off that has completely unlocked the world of simulation and computational science as we know it. You know, this incredible power of approximation has literally built our modern world. Everything from designing quieter cars to predicting the path of a hurricane. But it also leaves us with a pretty cool question to think about. As our computers get insanely powerful and new things like AI jump into the mix, what's the next great leap forward? Will we one day create a digital twin of something that's so accurate it's totally indistinguishable from the real thing? It's something to chew on. Thanks for joining me for this explainer.